Hello everyone. So in the last class, we started to discuss the equations of motion. We made sure we were in the continuum regime, and then we started with the continuity equation. We looked at what would happen to the continuity equation if the incompressible assumption was invoked. Then we moved on to the momentum equation, as you see on the slide here. So the momentum equation starts from Newton's second law, first principles of Newton's second law, where dp dt, rate of change of momentum, is the sum of all forces. And sum of all forces would mean surface forces plus body forces. So the body forces example would be gravity. We will neglect that for now and just focus on the surface forces. Surface forces would be of molecular origin because they are mainly related to friction and hence related to viscosity. Hence we are saying they are of molecular origin. So they are described by a symmetric stress tensor, a stress tensor that is symmetric. So now the momentum equation can be written as rho duj dt equals del xi of tau ij being the stress tensor which is symmetric. Any tensor, any symmetric stress tensor can be divided into two parts. One is an isotropic part which happens to be our pressure now, again independent of direction, so it is isotropic. And then the deviatoric part. So mu del ui del xj plus del uj del xi. So that's what we have. You substitute that into equation number 3 here. Then what do you get? What you get is rho duj dt. Okay. So then if I have, so I'm going to show that to you, I have rho duj dt equals del xi of tau ij, isn't it? Now your tau ij is p delta ij, as in Kronecker delta, plus mu times I have del ui del xj plus del uj del xi. In order to make the notation a little bit simpler, what I'll write this as p delta ij plus mu del j ui, isn't it? Another way of writing it, del I uj. Okay, so like this, and then this is del I tau ij. On the left hand side I have rho times del t uj plus uj del I uj. That is the convective term. Uj, no, I made a mistake here. So I'm going to erase this. I will have u dot del u, isn't it? U dot del u, so it would be ui del I uj. Ui del I uj equals del I tau ij. And instead of tau ij, now I will plug in p delta ij, the isotropic part and the deviatoric part. So then I have del I del I p delta ij, okay, plus mu del I del j ui plus del I uj. Now this Kronecker delta applied to the derivative, it becomes del jp. It becomes del jp because the Kronecker delta applied to del I becomes, you switch the indices and you get del Jp plus, then from here you can have mu. Now I can switch these two derivatives and then I'll have del J del I ui plus del I uj, and then there is a mu is on the outside. Now if I invoke the continuity, this is the continuity equation, again with the incompressible assumption. So incompressible flow, del dot u is equal to 0. In index notation, that is del I ui is equal to 0. So this part here would be equal to 0. In which case what I have is rho del t uj plus ui del I uj equals del jp plus mu del I uj. In vector notation, this becomes rho del u del t plus u dot del u. U is a vector here, equals del p plus mu del squared u, u being a vector. This is your Navier-Stokes equations with the incompressible assumption. That is how we could take del j or del I ui equal to 0, and plus it is Newtonian, of course, and that is why the mu, the viscosity, can come outside. So I hope that is clear. Now if I go to this equation, that is exactly what I have written. Rho, now I have just written it in terms of the material derivative, and of course we can do that because this right here is rho du dt, and that is exactly what I have here in equation 5. This is the Navier-Stokes equations, specifically the momentum equation. I hope that is clear. So we have the total derivative of the velocity on the left hand side, which is essentially the acceleration, and on the right side I really have sum of all forces. The forces coming from pressure and from viscous force, friction. So in order to solve this equation, we will need boundary conditions as well. And so the boundary conditions would be n dot u is equal to 0. That would be the impermeability condition. So nothing can penetrate. N dot u would be equal to 0. And then you also have the no slip boundary condition, meaning the fluid velocity on a solid surface, on a stationary solid surface, is 0. It's a no slip. So fluid doesn't slip. So then what you have is u minus n dot u. Remember, n is the unit normal to the surface. So that's the no slip boundary condition. Here you have the impermeability condition, as in nothing can penetrate through, and also the no slip boundary condition. If you have inviscid flow meaning no viscosity. If you have inviscid flow, then the Navier-Stokes equations would reduce to the Euler equations. In that case, what you will have is rho du dt is equal to minus del p. So the mu del squared u goes to 0, is approximately 0. Vanishing viscosity. Of course, that is not realistic, because if you don't have viscosity, if you don't have friction, you don't have a no slip boundary condition, you do not have fluid velocity on the surface being 0, and so you will not have a boundary layer in any flow that is involving a solid surface, which is unrealistic. However, this has been used for several test cases in order to analyze flows and to get a general idea about how flows would behave. The Euler equations has been used for years. Even to date, it has been used for different solving different problems. The Euler assumption. meaning the inviscid assumption. So what we are assuming then, okay, if we take the Euler equations, is that velocity on a solid surface is non-zero. So that your boundary conditions would have to be that. That's what I mean by tangential velocities at the wall would be non-zero in that case. Isn't it? So if I move on, I now have the continuity equation and the momentum equation. Now let me look at the role of pressure and also conserved scalars later, but let me start by looking at the pressure a little bit closely. So I have the incompressible assumption, and we are dealing with incompressible flows in this class mostly. So here del dot u is equal to 0, u is a vector. Divergence of velocity is equal to 0. In index notation, that is del I ui is equal to 0, isn't it? If for incompressible flows, the pressure and any isotropic stress actually can be bundled up into a body force, can be bundled up along with gravity, and we will see that in the next module. But that is the role of pressure here. It can be considered to be like a body force because there is no coupling between pressure and density. When I started this class, we talked about the definition of incompressibility, and one of the ways we defined it is that the density does not change with respect to pressure. So density is independent of pressure. It does not change with respect to pressure. So there is no connection between pressure and density. That is the actual definition of incompressibility. In such a scenario, the role of pressure is just an added body force. It has the same effect as a body force. So now if I take the divergence of the momentum equation, and here what I'm trying to do is I'm trying to come up with an equation for pressure. Because if you think about it, if I go back and look at my equations, I start with the continuity equation, I have continuity equation, and I have the momentum equation. Now let's think about this a little bit closely. I am looking at the role of pressure. So I'm going to write something here. I have continuity. This is an equation that looks like this with the incompressible assumption, is because that's what we are dealing with right now. I have del dot u is equal to 0. So this implies in index notation that is del I ui is equal to 0, which is the same as del u1 del x1 plus del u2 del x2 plus del u3 del x3 is equal to 0. So this is because my velocity vector is u1, u2 and u3, and my position vector x is x1, x2 and x3. So that is my continuity equation. Obviously this is just one equation. Then if I look at my momentum equation, I have in vector notation that is du dt equals minus del p plus mu del squared u. So in index notation that is del uj del t plus ui del uj del xi equals minus 1 over rho del jp plus mu del I uj. So there is a 1 over rho here. I'm sorry, actually just a correction here. This is minus del p. If this is minus del p and this is rho here. Okay, just to be correct, it is rho here. And I want to go back and make a correction. There is a minus del P here. So when I wrote here, there is a minus. This is supposed to be minus del P. So the stress term is minus P delta Ij. So that makes everything correct. There's a minus here, there's a minus here. And it is minus delta P. Minus del P. So this is what I have. And as you can see, this is a vector equation. This has 3 components. It's a vector equation, so it has 3 components. So I have altogether 4 equations. I have altogether 4 equations. And I have 4 unknowns, isn't it? 4 unknowns, which is what? U1, U2, U3 and P. These are my 4 unknowns. 4 equations and 4 unknowns. So I should be able to solve it. However, in the first equation, I do not have pressure. I have only velocity. And in the second equation, I have, as in the vector equation, I have only velocity. I have velocity and pressure here. So then how do I solve for pressure from here? Because the first equation does not have pressure. So I will need to obtain an additional equation for pressure. So this is what I do. I take the divergence of momentum equation. I take the divergence of the momentum equation. Then what I have is, I take the del J of equation 3, right? When I say equation 3, it is because there are 3 equations. That's why I'm calling it equation 3. So I take a del J of the 3 equations. And then what I have is, I will have del T of del J Uj. I can switch between the time derivative and the spatial derivative. Plus, I have del J Ui del I Uj. And then I will have minus 1 over rho. Actually, there wouldn't be a minus 1 over rho. It would be, the rho would be on the left hand side. So I would have the rho here, and then I would have del Jp, which is what again? Which is, now I've taken the divergence of it. So I would have del Jp minus, of course, plus mu times del I, sorry, I should have written del I, del J Uj. Look at what happens. I have the del J Uj here, which is equal to 0 because of incompressible. And I have the del J Uj here, which is again equal to 0 because of the incompressible assumption. So I have only 2 terms left, these 2. And what I have is del J Ui. So that is del Ui del Xj and del Uj del Xi is equal to minus del squared P. That is essentially what I'm getting here. Del squared P is minus rho del Ui del Xj del Uj del Xi, isn't it? If I look here, there is obviously a rho and then minus del squared P. So rho del Ui del Xj del Uj del Xi is minus del squared P. That is what I have. This is your Poisson's equation. This Poisson's equation, with the help of the fact that it satisfies continuity, can be used to solve for pressure. So now you have the momentum equation where you solve for the velocity, you assume some pressure, then you correct the pressure using this Poisson's equation. That is generally the way these equations are solved. So the Poisson's equation is another form of the momentum equation with the continuity assumption invoked. So you took the divergence of the momentum equation, and what happened when you took the divergence? The local acceleration term and the viscous term reduced to zero, isn't it? The local acceleration term and the viscous term reduced to zero because of the incompressibility assumption. And then what happened is you are left with the nonlinear term and the pressure term. That is essentially what you end up getting. The Poisson equation would have Laplacian of pressure on the left hand side. So this is a Laplacian of pressure. And the right hand side is of course a nonlinear term. You have minus rho del ui del xj and del uj del xi. This is the Poisson equation that is used for solving the pressure. Now, so we looked at the role of pressure. Now let's look at the role of the conserved scalar. So an example of a conserved scalar or a passive scalar is, say, mixture fraction. When you have species that are mixing, when you have flows that involve mixing. Another conserved scalar or a passive scalar is temperature. So let's say you have a fluid that is flowing in a pipe that is probably coming in hot, and the pipe is used to, say, cool the fluid. In that case, there will be heat transfer. The temperature of the fluid will change. The temperature of the pipe might also change, the pipe surface. Temperature here is a passive scalar. So example of passive scalar is temperature. Now what is the other type? Let's say you have an active scalar. Active scalar would be, say, species mass fraction in reactions during reactions, chemical reactions. So I'm talking about a conserved scalar now. So if I have a conserved scalar, this is what my equation looks like. I have the total derivative of the conserved scalar, let me call that phi, equals gamma del squared phi. This is a diffusion term. On the left hand side is the total derivative of the conserved scalar. So I'll have del phi del t plus u dot del phi. Okay, here u is again a vector. This is the advection of the conserved scalar, advection of the passive scalar, equals gamma, which is mass diffusivity, del squared phi. Gamma here is the mass diffusivity. If this was a temperature equation, it's like the heat transfer equation. We had taken this example earlier. In that case, gamma would be a thermal diffusivity. In this particular case, it is a mass diffusivity. So here what we have is d phi dt is equal to gamma del squared phi. Now, you have the advection on the left hand side and then diffusion on the right hand side. Remember, unlike what we had for the continuity and momentum, if we are dealing with some kind of a mass fraction or even temperature, right, like a mixture fraction or temperature, like a conserved scalar, it has to satisfy certain boundedness. Like the mixture fraction usually is between 0 and 1. Even temperature cannot go above a certain limit. The maximum temperature of, say, the bounded wall, it cannot go beyond that. It has to stay within the limits, or the lowest temperature of the bounded wall. So it has to satisfy some kind of boundedness, which is phi min to phi max. So that could be, for example, between 0 and 1. So this is an example of a conserved scalar, a conserved passive scalar. So in certain scenarios, this could also be here. So we looked at different equations, right? We looked at the continuity and the momentum equation. The continuity equation comes from the conservation of mass, from first principles. Mass can neither be created nor destroyed. So it comes from the first principles. The momentum equation comes from Newton's second law, which is again based on first principles. Some rate of change of momentum is sum of all forces. We took surface forces and body forces initially, and then we assumed the body forces to be neglected for now, and we considered only surface forces. Then we took the stress tensor, and we equated that to an isotropic part, which is the pressure, and a deviatoric part, which is what you see here. We put that into the momentum equation, and we got the momentum equation in this form with the incompressible assumption and the Newtonian assumption. And we got our momentum equation in this form. So rho du dt is minus del p mu del square du. Now, in order to solve for pressure in incompressible flows, we need an additional equation. That is how we took the divergence of the momentum equation and obtained the Poisson's equation. So we had continuity, momentum, the Poisson's equation. The Poisson's equation, where you have the Laplacian of pressure, can be used to solve for the pressure. Then finally we had the equation for conserved scalar. So this is not there in every scenario, but let's say the fluid is coming in hot, there is heat transfer involved. This is an equation that you would have to consider. So these are the equations of motion that we are going to solve. In the next class, what we are going to do is we are going to consider an additional equation, which is again a derived equation, which is the vorticity transport equation. And we will derive that in the next class. Thank you.